Okay, so before that, I'd like to contextualize what we actually do in my lab and what our mission is. So we're really looking at multi-agent systems from the perspective that the next wave of computing is all going to be about agents that communicate and coordinate. And that's really being driven by the developments that we have now in AI, communications, and mobile computing jointly. So that being said, it's a future-proof mission, but it's actually also really timely because we're seeing how robots are now pretty pervasive. They're being used in various applications where they're distributed and also connected. And they're solving a variety of different tasks for us, especially in the domains of factory automation, logistics, and also increasingly outdoors and more unstructured environments. This being said, we're not really seeing the deployment of multi-agent, multi-robot systems at larger scales in more complex and unstructured environments. And that is really where our research mission and vision fits in. Let me organize this a little bit for you according to these two axes. So this is here to crystallize where I believe the research frontiers really lie. So on the vertical axis, you see here the ability or capability of agents to deal with partial information problems. So less information is given to individual agents. And on the x-axis, I'm representing problems that are more complicated, more complex in scale, higher numbers of degrees of freedom. The agents are potentially heterogeneous, and the tasks overall are more complicated to solve. So it turns out that we have really good solvers for problems that are either relatively small in scale or that are fully observable. But what's really difficult to solve for us to date are the problems that I'm calling online scalable that fit within this regime. So these are kinds of problems where we're looking at highly dynamic environments, things are changing in real time, they're potentially high dimensional, complex domains, agents are potentially heterogeneous. And all the while, we're trying to solve problems where the agents have to cooperate and solve and respect global objectives. And we want them to solve these problems relying only on information dissemination schemes that are ideally decentralized and based on point-to-point interactions. So doing all of this together is a really difficult problem. And first principles models and solvers have not really been able to satisfy solutions to this domain. And this is why my lab for the last 6-7 years, we've been looking at end-to-end data-driven solutions to do this, and also a couple of hybrid paradigms. And I'm going to talk to you a little bit about how we're doing this. So I begin with just describing how we're going about modeling this. So we're looking at the simplest scale at 2 different agents. And we begin by saying we're going to model how these 2 agents interact. And we do this by assuming that we have some function phi that represents or models this interaction for us. So this function phi is basically telling us how the observation of an agent J influences the action of a robot I. And what's nice about how we go about designing this is that we're going to make sure that this function phi is scalable. So it's capable of aggregating information coming in from a neighborhood and feeding that aggregated information to my robot I that is going to be using this collective context to make downstream decisions with respect to its downstream tasks. Okay, so we go about and we formalize this in the form of a graph neural network. So I'm showing you here one of the most general ways that you can write down a graph neural network. And so basically what we're doing here is a couple of things. We're imposing on our multi-agent system a graph abstraction. So the agents are nodes, the robots are nodes in these systems, and the interaction topology is basically being described by a graph. So that's our inductive bias that is going to help us organize the data so that we can learn from it effectively. And then this function phi now uses 2 mechanisms inside of this formalism. The first important one is the aggregation mechanism. And the second one is the one that's going to describe the interaction topology. And there are various ways that you can go about instantiating these 2 operators. One of the simplest formalisms is in the form of graph convolutional neural network. And to make this very concrete for you here, I'll just step you through it. So the graph convolutional neural network basically assumes that the aggregation mechanism is a sum. and the interaction topology is given to us by an adjacency matrix. And using those two instantiations, we can write this down very nicely in matrix form. And you can see on the right-hand side here, that equation, it beautifully exposes the learnable parameters of our system in matrix denoted by W here. So A is our adjacency matrix and Z would be our interaction features. And so W are now the parameters that we're going to be trying to learn here as we collect our data and train our systems with respect to some downstream objective. What we can also do, and that's the key thing here, beyond just modeling the interaction, we can also synthesize the interaction. And what I mean by synthesizing here is I can literally construct communication messages that the agents then can go and send each other in order to satisfy or optimize some sort of objective. And so what I basically do is I string together these elements, and what it does for me is that I'm basically going to be sending communication messages where the policies of the robots that they're going to be running, or these communication strategies, are being conditioned on neighborhood information. And so that's really key, because now I have agents that are they're able to act with respect to what they're learning about their environment through the other agents that are observing these things around them. And this construct essentially is going to help the agents get over the partial observability that is limiting them if they were to be acting only alone. So here, just to summarize, this policy, what it's doing for me, this interaction policy, is allowing me to learn how to decode outgoing information and process incoming information. One of our earliest examples of success was in solving the multi-agent pathfinding problem. So in the multi-agent domain, this is actually a really excellent example to work on. It's an NP-hard problem. It's difficult to solve. NP-hard here, what it means for us is basically as I scale my system and the number of agents, it becomes harder to solve, exponential in the number of agents. So what we instead are doing is we're saying every agent is going to be running a solution to the system locally. So we're solving the problem in constant time. And the amazing thing here is that empirically, the performance is near optimal, and we also have extremely high success rates. So the cool thing here is it's an NP-hard problem, but we're solving it extremely effectively with constant time solvers that are running locally on every individual agent. And we're doing this essentially because the agents are aggregating global state information locally through the power of this learned communication policy that we've trained by copying optimal experts in an imitation learning paradigm. So we're not quite there yet. We haven't solved NP-hard problems in constant time. There are a couple of things that are really crucial here that we're still working on. Most importantly, we don't have guarantees on optimality because these are currently just data-driven approaches for which we don't have relevant guarantees, and we don't have guarantees of completeness either. And those are two really important things that we're still working on in order to make these things tractable and really deployable into the real world. That being said, it's strong evidence that these kinds of approaches work really well for very hard multi-agent problems. Now, up to now, I've only talked about learning or devising strategies that are deployed homogeneously across our different agents. So what does that actually mean? So that means that for a given observation, all the agents are going to take the same action. So that's what a homogeneous policy does. And homogeneity is really interesting for a number of reasons. It's interesting because we can do parameter sharing. It's interesting because they're permutation equivariant. It's extremely sample efficient. And we can even emulate heterogeneity by using a couple of tricks, such as inferred context or explicit indexing. So what is heterogeneity in that case? Well, heterogeneity basically means if I have two different agents that take the same observation, they're actually going to take different actions. So that's a truly heterogeneous policy. More from the practical side of things, what that means for us is that we're not able to do parameter sharing. We can do decentralized training, but because we don't have a permutation equivariant scheme and our observation space explodes, these systems for training become actually quite complex and expensive to train. So is heterogeneity actually worth it? And I'm getting into the core of my talk, and I want to first talk a little bit about why heterogeneity is really crucial to solving a couple of really difficult problems, and then I'll go into a couple of the methods that we developed in order to facilitate heterogeneous multi-agent, multi-robot policies. So let's talk a little bit about why, and I'm going to start with examples from nature. So nature has evolved to develop heterogeneity and also maintain heterogeneity in its communities. Here are two examples. So we know from ant species that they've evolved anatomical differences that make a lot of sense because the specialization is crucial to maintaining life in their colonies. So in ant species, we have major ants that do things such as guarding nest entrances, and the minor ants that are slightly smaller do things like self-grooming or cleaning up the nests. And in bee colonies, we see heterogeneity evolving throughout the lifespan of the bees in the colonies, which is also really interesting. So as they grow older, they do more and more, in this case, patrolling, and the younger bees would do more, say, less critical roles, such as cleaning up the cells, etc. And nature has figured out that this is a really effective way to function. So that and other examples have really spurred engineers and scientists like us to look more deeply into heterogeneity and how to facilitate this for all kinds of problems. And here are a couple of examples that we have actually found that for which heterogeneity makes sense. So heterogeneity makes sense when you have problems that are complex in the coordination domain of things, where it's just really simple to solve when you have heterogeneous controllers, when you have roles that require specialization, for example, in games such as football, or tasks that are a little bit more nitty-gritty, where it's easier to train the agent to do different things as a function of the same observation. And then, of course, highly complex coordination problems in the NP-hard domain, where heterogeneity helps you resolve these or disentangle these complexities. And there's also some work that we've been doing in my lab. Oh, there's even music. where we're deploying, yeah, wait a second. And so that was a couple of, that was a bit of work from my lab where we're deploying quad rotors as well as ground robots in a complex multi-agent problem. You could imagine these, this kind of emulating a pick-and-place type scenario in warehouse, et cetera. And clearly those were heterogeneous systems because we have two different platforms trying to solve the problem in three-dimensional space. So those are just a couple of motivational examples, and I want to take a deeper dive into the navigation problem and explain to you on hand of that example where and how heterogeneity comes into play and help us solve the complexities. So taking a look at the pathfinding problem, what is so hard about it? Well, what's hard about it is that if we want to solve these problems in a decoupled way, which essentially relaxes the complexity of the problem and disentangles the NP hardness from the problem, the thing is that decoupled solvers aren't complete. So in the example that I'm showing you here, if the green agent decides to move towards its goal position, then the blue agent finds itself blocked, and we have a deadlock solution where the blue agent will never be able to reach its goal. However, if we take a coupled approach, then basically the planning happens in joint state space, and the green agent is actually going to wait and stay put so that the blue agent can cross its path and reach its goal location, and then only will the green agent move. But in order to find the solution, you have to represent in joint state space, and hence the complexity of the planners here. So the compounding challenges that we're actually facing is we want to be able to do this with decoupled decentralized controllers in the continuous domain, in cluttered environments, and we want to be able to relax reliance on centralized controllers that could essentially do the coupled planning for us. So what is the best we can do to date? Well, if we look at controllers in the continuous domain, this is an example of one. So control Lyapunov combined with control barrier functions. They allow us to execute these kinds of things in the continuous domain in cluttered environments. Now, we take an off-the-shelf solver, we deploy it onto our robots, we tell the robots, you're going to navigate this passage, this constricted scenario, and you're going to end up in your predefined destinations on the other side of this constriction. But it turns out that the robots can't actually solve this problem. And they start moving, but then they kind of come into this deadlock position in front of the passageway. So we're like, well, what's going on here? Why can't they solve this? These are state-of-the-art controllers. These are recent papers. This should work out of the box. And so we take a closer look at the actual formalism here, and that kind of reveals a couple of interesting things to us. So just to step you through this, what is it that we're actually trying to do here? Well, we begin by modeling the system with the simplest possible dynamics model. We have single integrator dynamics for our robot. And the optimization problem here is very simple. We're trying to minimize control effort for the robot. We're solving a quadratic program at every time step that does this minimization, subject to two constraints. And the two constraints are basically potential functions. One is a repulsive one, that is our control barrier function, saying, well, you have this potential when you're getting closer to objects or other agents, you're being repulsed. And the other one is an attractive potential, which basically guarantees that I will always converge towards my goal location. Right? So those are my two constraints. And if we look a little closer at my control barrier constraint, the repulsive one, we see that it relies on two hyperparameters, eta and zeta. And these two hyperparameters, normally, so this is what is done in state-of-the-art literature, they're tuned a priori. And you have to tune these usually in simulation because you don't have access to your operational domain a priori. And you'll do the best effort attempt at estimating what those hyperparameters should be set to so that your systems perform reliably in the real world. Now, if you set these parameters to conservatively, what happens is that your robots will be taking very inefficient trajectories around your other obstacles and agents. If you set them too aggressively, you'll end up with infeasible controls and you might be violating your plant dynamics. Okay? So it's very critical that you find the right values for these two hyperparameters before you deploy your systems. Now, the problem is these are usually set homogeneously for all your robots, and they're fixed. They can't vary throughout time. And that is the issue that we've encountered before. So when things get hairy, those two parameters cannot adapt. So our idea was to take a graph neural network to output these two parameters in real time as a function of what the robots are observing in their immediate vicinity, in their immediate neighborhoods. And we do this first in simulation, and we can see here on the right-hand side how these two parameters are varying throughout time as a function of what the robots are seeing. And it leads to successful completion of tasks in very tight and cluttered environments. Now, even if we would take the parameters from these arguably valid ranges and deploy them homogeneously and fixed across our robots, we see exactly what we thought would happen and we saw happen before, which is either you're too conservative and you can't circumnavigate effectively, or you're too aggressive and you end up in deadlock again. Okay? So this is the counterexample showing us that, well, we cannot just take static hyperparameters and deploy this. So we really do need something that is heterogeneous and time varying across time in scenarios which are very complex. And so now we take this graph neural network time varying based approach and we deploy it onto our case study that I showed you before. And now we have a successful completion of our task that effectively solves the problem. And it does so because this time varying approach now that is heterogeneous across the robots implicitly is allowing them to prioritize their passageway through this constricted scenario due to the facilitation of heterogeneity and reaction to any individual robot situation at any given point in time. So this was really great for us to see and validating this this assumption that we need to allow the robots to fine-tune their behaviors as a function of their own individual situations. And there's another really interesting scenario that motivated the use of heterogeneity for us. And this was in the realm of robustness to zero shots of sim to real transfer of policies to the real world. So we start with heterogeneity. With heterogeneous controllers in this problem where we have two robots that basically see the same thing, and they're just being rewarded for reaching the other side of this corridor scenario, right? And they have to make this navigation, so they have to do this passage, this coordinated passage, by using only relative information as their observation. So they only know something about each other, but they don't actually know what their labeled goal position is supposed to be. So they learn. They're rewarded as a function of them reaching these goal positions only. So training heterogeneous policies in simulation and then transferring this to the real world works really nicely and works without a glitch. If we do the same thing with our homogeneous counterpart in simulation, where the robots are inferring their roles as a function of their relative context, in simulation, this works really nicely, no problems there. And we do the same thing, we take these policies, transfer them zero shot to the real robot platforms. And it turns out that in this situation, the robots start to oscillate around the midpoint and they don't really know what to do anymore. And the reason for this is simply the introduction of just ever so slight amounts of real world noise, which is not controlled in this case, it just happens to be, is enough to throw off these robots from what they learned in simulation, and they no longer know what they're supposed to be doing robustly anymore. And so heterogeneity here, what it brings us is really strong robustness to noise that you would otherwise encounter in the real world. And the robustness comes through because the robots have specialized due to the fact that they're allowed to learn different policies to the specific roles that they have to take up when they're then acting in these particular tasks. So that motivates the need for mechanisms that allow us to execute heterogeneous behaviors. But if we now want to engineer heterogeneity in a more precise and controlled way, we need two key elements. And the first part of this mechanism design is we need to be able to measure heterogeneity. So we started by saying, okay, there were a couple of measures out there, but none of them really satisfied our needs. And so we went about designing a new heterogeneity measure, which we call system neural diversity. And what it essentially does is it measures behavioral dispersion of the agents in state action space. And basically, what the properties are of our SND metric are that, well, it measures behavior dispersion, it's invariant to the number of equidistant agents, and it's also able to measure behavioral redundancy. So this formula here actually depends on one key function, which is Dij. And Dij is our distance measure that tells me how far apart two different agents are. So Dij is actually very elegant, and it allows me to say something about these two agents based on the premise that, well, my policies are essentially multivariate Gaussians, and I can compute this Dij in closed form if I also know how to solve this integral, whereby here we're actually using as a divergence measure the Wasserstein metric. Now, the key thing here is that in order to evaluate the distance between two agents, I need to also evaluate the whole observation space, which is where this integral comes in. And so practically how we do this, in order to evaluate how these policies diverge over observation space, is during execution or through policy rollouts, we're doing a Monte Carlo sampling of these values throughout the execution of these policies on any given task that we're running the system on. And so this is how we compute our SND. And we then went about to see, well, before we actually try to control for diversity, what does SND by itself actually tell us about what's happening with our systems? And so we came up with this interesting example where we have two agents that have to fly with in a formation that is fixed with respect to the distance in between the two agents. So the two agents have to maintain a certain distance, but they can fly in any configuration with respect to each other. So next to each other or behind each other. And the reward that they're actually receiving is going to be inversely proportional to the joint amount of wind that they perceive in the system. The wind, however, is not always turned on. And the agents don't actually know that they're anatomically different. So there's one agent that has a triangular formation that can deflect wind, and the other one that cannot deflect wind and is round. So you can already imagine that the round agent should optimally be placed behind the deflecting agent, and that's when the system as a whole is going to reap the highest rewards. But they don't actually know that unless they experience it, and they experience the higher rewards in those settings. So we train our systems. So orange here is homogeneous and blue is heterogeneous. And we can see how when there's no wind, they both perform equally. And as soon as the wind starts blowing, the heterogeneous policy starts outperforming the homogeneous one because it allows the agents to specialize in these two different roles, right? So the deflecting one goes up on the top and the circular agent is in the bottom. And here the heterogeneity of the system allows this clear difference in performance. As soon as the wind stops, both policies perform the same. And as soon as we reinstantiate the wind, we have the difference again. But the key difference, if you look at how the policy evolves throughout time, is that the second time the wind is turned on, there is no more learning curve for the heterogeneity. For the heterogeneous counterpart, it immediately performs again at the same level it left off when the wind stopped blowing. Now note that this is not inference time, this is training. And so if we look at how the SND evolves throughout time, what we can see is that during the period where we actually have no wind, The agents remember the diversity that they learned when the wind was blowing. And this diversity, although it's starting to go down a little bit, it still is there. And the agents remember that this was a skill they learned that was really critical for them to counteract the disturbance that they were facing before. And so we're calling this latent resilience. The agents have learned to be resilient in a and it's latent now because it's not being used. But as soon as the disruption occurs again, that latent resilience comes in really handy because the agents know how to act in order to perform better in these given situations. And we can see the exact same thing in another scenario where the agents have to learn to navigate these two gates, where the disruption in this case is a narrowing of one of the two gates that they have to fit through. And again, here the agents, they don't observe their own size, so they don't know that one is smaller than the other. And only the small agent actually fits through through the gate that is narrowing over time. And through specialization, the small one learns it always has to go through the left, and the big one learns it has to go through the right one. And again, we see this latent resilience when the gap widens, that comes into play again as soon as the disruption occurs again. So this is really cool, and SND came in handy here because it's now showing us through this measure that we have this thing that we can call latent resilience, which we otherwise would not have had insight to without the measure of diversity in the system. So coming on to the final bit of my talk, we've seen that heterogeneity is really helpful and it can be useful in multi-agent systems, but now we want to be able to control for it, to create a system that is heterogeneous to a specific amount of, or budget of heterogeneity that we give our system. So what does this actually mean? So we came up with an algorithm that has as its goal to distribute a diversity budget over observation space. And I'll talk a little bit more about what that means in just a second. It's going to exploit our SND metric to control the diversity. So the set point that we give the system that it's going to control to is going to be given by our SND metric. And different to a lot of prior work, we're not simply going to be boosting diversity, we're going to be controlling it to that exact value that we want the agents to reach in terms of their diversity. And the final thing that we do in terms of practicalities is that we're actually maintaining n+1 networks in order to, where one network is actually representing the homogeneous part of the policies, and very small networks are going to represent the heterogeneous per agent bits of the individual policies. And that saves us a lot in terms of parameters that we're going to have to be learning. So the policy representation here, just to be clear, is there's a homogeneous part and a heterogeneous per agent part that is not shared. So how do we train the system? So the key thing here is that at every single training iteration, we're going to be guaranteeing the SND that we want. So we have a desired SND, and we're going to be guaranteeing that this SND is met at every training iteration. So even though performance is going to be evolving throughout training, SND will be the same and will be the desired level from the get-go. And we do this very simply by scaling the agent policies to meet the desired SND value that we set the system at the outset. And we simply do this by rescaling the values that we have at every training iteration. So essentially normalizing the deviation of the per agent policies in order to match the desired SND across the system. So this is a structural change in the learning algorithm that allows us to guarantee a desired heterogeneity. And now we look at, okay, as we increase or decrease heterogeneity in our system, what does this actually mean? So I'm going to describe that on hand of this very simple example here. So we have two agents that have the same observation and have to, as a function of this same observation, they have to do two different things. So they can only succeed if they actually have heterogeneous behaviors here. So what is it that they have to do? They have to solve the very simple task of reaching the goal that has the same color as they do, but they don't know what their color is. Right? So the red agent has to reach the red goal, the blue agent has to reach the blue goal, and that's when they're going to get rewarded in the system. So obviously, if they have homogeneous controllers, they're not going to be able to distinguish where they're going, and homogeneous controllers actually cannot solve this task. As we increase diversity, the red agent will learn that when it's pointing its goal, that it'll move in one direction, and the blue agent will learn to move in the other direction when it's progressing towards its goal. And the plot here, what it's showing you is how the diversity is distributed over observation space. And so intuitively, what you can see here is in locations that are placed in between the two goals, which is where diversity has to be highest, right? Because the red has to go one direction and the blue agent has to go in the other direction. That's where the algorithm has learned to place the highest diversity in terms of the outputted action as a function of the observation. And as we increase the diversity, you see how this budget is being spread out more aggressively in the zones that are located in between the two goals. But as we go to a completely unconstrained diversity paradigm, you see that the diversity budget is not being placed very wisely anymore. And even you see diverse controllers acting in areas where it's not relevant anymore and it becoming very unstructured. So this here motivates the need for both having heterogeneity, but also controlling it to a specific level that is just right for the given underlying task. So what can we do with this? So we started with a couple of simple simulations at first, where we showed, for example, in the case of field sampling, where we want the agents to distribute as quickly as possible and cover a given arena. If you have homogeneous controllers, they end up doing kind of the same thing. But if you enforce heterogeneity from the get-go, they're much more effective in distributing in a more strategic way across the environment and covering it more quickly as a team. Same goes for dispersion, where agents have to go and reach different goals simultaneously. Heterogeneous controllers allow the agents to learn this more effectively. And really cool in the domain of games, where in this particular case, we're looking at a predator-prey scenario. The predators here, so the two red agents are predators, they learn different strategies that jointly work together to catch the prey more effectively. So in the top example, we see an example of cornering, where one agent kind of goes and tries to corner the other agent, while the other one then comes in and actually tags the prey. And in the bottom one, we see an example of ambushing, where one will kind of be hovering around and the other one chasing the prey, so that the tag operation again is executed more effectively. And you can only learn these kinds of behaviors if you facilitate predators to learn different strategies that then jointly work together to solve the problems more effectively. So we were really excited about these emergent behaviors that were only facilitated because we enforced heterogeneity in the controllers. And the last example I want to show you is something that that we're really, really excited about, that really blew our minds. We thought we would think about football as an example where we think heterogeneity makes sense, but we wanted our AI algorithm to kind of confirm our hypothesis. And so what we did here is, well, we have a red team that is being controlled by homogeneous controllers, and the blue team was the one that was being controlled by our heterogeneous learning paradigm. And we thought, well, we're going to just tell the system basically nothing. So no coded priors, no nothing at all, and we're just rewarding it for goals. That's it. That's all the information we gave to the system. And we said, you're going to learn this with a diverse strategy, but we're not going to tell you what you're going to do. You're just going to be rewarded for goals. And as I play this out, you'll observe the behavior that the blue team, so the heterogeneous team, learned is really interesting. We have the emergence of a goalkeeper. We have the emergence of defenders, and we have the emergence of attackers. And well, what's really cool here is that we are essentially validating the design that humans came up with for designing football teams. But this was completely by our AI, simply by enforcing heterogeneity in controllers. So these are some upcoming results that we're really excited about. So just before I conclude, I just want to acknowledge a lot of the work that my team does in developing the tools and the platforms that are necessary to do this kind of research. So we have a lot of work on software tools and libraries, Benchmark and VMAS, which is our simulator, as well as all the platforms that we use in my lab, which are essentially designed in-house using off-the-shelf components that facilitate the kinds of things that we do. Summarizing what I talked about today, so I hope I've motivated the need for more effort into looking into diversity and heterogeneity in multi-agent systems. But there are a lot of problems that still remain to be solved. One of the most important problems is actually identifying for any given downstream task, what is the optimal amount of heterogeneity and how can one find that for any given problem or any given task? And in which environments do heterogeneous teams actually thrive? And maybe there are some in which homogeneous teams are actually the better choice. And understanding and being able to distinguish those two types of environments from each other, we believe is also a very valid research question to look into. Longer horizon questions look into guaranteed and interpretable robot behaviors, especially as we're thinking of using more and more black box and data-driven models. Continual onboard learning is something that we're very interested in, as well as inference on resource-constrained platforms that have to run these models in real time, and also thinking more about taking our robot systems outside of our labs into the outdoors. With that, I'd like to acknowledge my team, whose work I have presented today, as well as all of my sponsors, for whose funding I'm very grateful for. And I'd like to thank you for your attention. Happy to take any questions.